Now, the way that MATLAB works in this is what it's going to do is it's going to set up a routine, and it's going to set up an iteration routine. It's going to start iterating towards a solution. It's not shooting. It just says, in fact, you get to give it a guess as well. Okay? Now, if you're a really bad guesser and you don't know anything about it, you can just say, I'll guess 0, because that's a pretty simple guess. But that also is a problem, right? It's presuming that you might actually kind of know a little bit about the problem, which you maybe hope you do. So we'll do a little harder problem after this. In this case, there's one solution, and it turns out I don't have to be a very good guesser at all. This is a very simple problem. So let's go ahead and solve this, and then we'll roid it up for the next problem. Okay? All right? Yep. So what you guess the solutions not at 0, but remember, there's no time in this problem. You just guess what's y1 and what's y2. I don't know. They're supposed to satisfy these boundaries. I'm just going to assume they're 0. That's the easiest guess. I'm going to say that y1 is 0, and you can enter anything you want. You can guess e to the x minus 3 sine x times 5 plus log 2 divided by 3 plus x. That could be your guess. All right. That's hard. Okay, so we'll just guess simple things like zeros. In fact, actually, if you look at the iteration procedures of MATLAB, MATLAB always just guesses 0. Like, why would you guess something harder than 0 if you don't know what you're looking for? So you start off with a good safe guess like 0 and see what you get. And start going from there. All right. So let's pull up MATLAB here, and I can picture. Okay. And could I have lights down in front? Do you see that? All right. And we'll try to film. Yeah. So if we could keep. Oh, can we get the screens going in the back? Are both TVs dead? You guys got me? Okay, awesome. And if you could mostly, I guess, film my computer. Awesome. So let's go over here, pull up my MATLAB. There's my MATLAB. All right, so there you go. Beautiful. There's my command window in MATLAB. Who loves that? Isn't that nice? Oh, it's like a blank slate which an artist would come to and program something. Okay, you ready? We're going to program this problem. And so let's open a new file. New M file. Okay. Here we go. So, first of all, this isn't so hard, actually. Let me give you the command. So, let's start off here. Oh, no problem. Will, I know. Without Will's, he's always kicking it. All right, here we go. This is easy because I know those commands really well. And we can start here. That's our guarantee of a blank slate. And let me tell you what the command is. Let me just give it to you here, and then we'll talk about what you need here for it. There's the basic command structure. Let's walk it through what this means. So I'll do it right here on my prompt so that people at home can see. I'm going to highlight that piece right there. So first of all, the command, the code, just like OD45, the code is called bvp4c. BVP standing for boundary value problem, turns out. 4, what do you think the 4 is for? 4 is for? Yes, exactly. 4th order. I don't know why the C is there. Anyway, 4th order boundary value problem solver. So it's going to try to give you accurate solutions with a 4th order scheme. Okay? It's going to use a 4th order scheme, but remember, the tolerance it's going to give you is already set. The default almost on anything in MATLAB is 10 to the minus 6. Okay? So your accuracy or your tolerance is 10 to the minus 6. It's going to use a 4th order routine to get down to 10 minus 6 for you. Okay? All right. Now, what do you need? This is going to call a function. So this, you can call a function in two ways. You can put it in quotes like we did last time, or you can say at, and then you call this bvp right-hand side dot m. And what is this? bvp right-hand side, this is the right-hand side of our system of equations. So we're going to build a function that just simply has the right-hand side. Okay, we already know how to do that because we did it in OD45. So it's easy. This bvp4c, so I think about it, bvp, boundary conditions. So you're going to put in these functions that are supposed to be 0. This is where the boundary condition information is contained. What do you think inish means? That's your guess for the solution. Okay? So that's it. You give it the equations, you give it the boundary conditions, and you give it a guess. And that's how it works. Okay? Now, we're going to do a little bit more here. This is actually, so what does it give out to you? Solve, solution. So the solution is some kind of functional representation of the solution. What it does is it iterates, gets the solution. And what you want to do with this solution is to evaluate the solution. You actually have to still use some of the MATLAB functionality. Okay, you have to interpret the way this data is structured for you. And so first of all, let's decide how we want to plot our data. I'm going to make a vector x, which is a linear space that goes from 1 to 3 in 100 points. Okay? So that's the linspace command makes a linear space, so it goes from 1 to 3, chops it up into 100 points. So I got the 100 points there for my domain. And that's x. And what I want to do now is I want to evaluate the solution at those 100 points. So my boundary solution would just, I would throw this in here. I would take my solution representation and evaluate it at the different x values. This is how this thing works. Sol is it's a certain data format that this bvp4c will spit out towards you. And deval evaluates it for you. Okay?
So you can't deal with Sol independently.
You can, but you're going to have to write a routine then to deal with it independently. And the point is, deval already is written for you. It already knows how to handle it. You just tell me the points you want it, and it'll do it for you. It's a little bit like when you do interpolation. If you do an interpolation of a function, or if you do a curve fit, it doesn't give you the points. It just says, I have all the coefficients of the fitting parameters. Tell me where you want to do this thing. So this is a polyfit and a polyval. Polyval takes the input from polyfit, which is a polynomial fit, let's say, to data, and polyval then evaluates it. It's the same thing here. You get out your solution, which when you want to evaluate it, deval does it for you. And it creates a vector, BS, boundary solution, with 100 points between 1 and negative 3. And then you could just so plot x versus BS. So that's the basic structure. Now, a couple things I want to comment on is this inish isn't as trivial as you might think. You might think, hey, I can put in just a vector there of a guess or something like that. Well, it's not that easy. bvp4c is expecting a certain format structure. And the way you get that format structure is by using bvp inish, which is another code. So there's a little bit of pieces here. But once you get them all together, and we're going to build it all up, it's really actually really nice to use. This thing's actually pretty amazing, I would say. Okay? So inish is going to be, we're going to have to call this thing called bvp inish. So initialize the boundary value problem. And what you need to do here, and we're going to do something very simple, is you first initialize by saying, what I'm going to do is make a linear space with 10 points, and I'm going to get 0 and 0 for y1 and y2. So what you give it initially, and this is kind of interesting the way this works, you give it an initial mesh. So you're going to say, I want you to evaluate this boundary value problem. I'm going to initially do 10 points. I'm going to just take this domain from 1 to 3. chop it up into 10 points. And by the way, what are the values of y1 and y2 at those 10 points? Well, right now I'm going to make them 0. And what it's going to do is going to say, okay, so great, you gave me a guess with a number of points. What it's going to do is go in there now, and it's going to start to iterate, and it will pick what it wants to have as a dx. Remember, I made this comment. It doesn't trust you to pick the right dx's, right? It's going to pick the right dx's. It's going to pick the right mesh so that what? So that it gets a solution that is 10 to the minus 6 accurate. That's it. Using a fourth order scheme. What was that? We'll do that in the next. Okay, so we're going to do this example here as a guess. Yes? 10 points totally made up. I could pick a million. Pick 2. And in fact, to some extent, for this problem it's trivial, but let me make the following comment. Probably the most important line of the whole code is right there. If you have a complicated problem, a nonlinear problem, you don't know how many solutions you have, you don't know maybe where to guess. Everything hinges on this, upon you being able to provide a reasonable guess. Okay, so that's, everything really hinges here. The rest of this is sort of trivial. The rest of this is, this thing just iterates forward, tries to find a solution for you. But remember what I said about the guarantee about convergence. Newton's method is guaranteed to converge, provided you're sufficiently close. So sufficiently close may mean a lot of things to a lot of people. But really what that means to you in practice is I'm solving a nonlinear problem. You better be a good guesser. Okay? And oftentimes this comes with experience about the problem. I'm kind of looking for these kind of solutions. I know they should probably exist. You would guess those kind of solutions. So we're going to do that next. But right now we're just going to say I have no idea what it looks like. Let's just guess 0, 0. And there you go. So this is the outside of the code. So file, save as. We'll just save this as something. No, solution across the whole thing. 0, y1 and y2 across the whole interval. I haven't guessed anything as boundaries. You only get to guess what the solution looks like, y1 and y2 across the whole thing. All right, we'll do that. Okay, now if you see here, I have 2 function calls, to this and to this. And let's make these a little easier. Let's call right-hand side bvp and bc bvp. I'm going to change those around. Okay, so first of all, let's go File, New, mFile, Function. I need to calculate some right-hand side of, what do I call it? Right-hand side bvp, right? So this is what I'm going to do. I'm going to calculate this. And what comes in here are the x values and the y values. I changed it, right? Yeah. Okay, so what I do is I'm going to come in here, and I have x and y. Now this thing already knows it's working initially with the domain with 10 points, right? And that's my x. And what it's going to do is change that domain around, start working towards what it wants. But this x is coming outside. Initially, it's 10 points. And the y values initially are all zeros. That's what comes in, and now it's going to start iterating on that. So this vector y has y1 and y2 in it. And so all we have to do is put our right-hand side in there, and our right-hand side is just simply y2, and then minus 3 times y2 minus 6 times y1 plus 5. And that was right behind that board. And if you need me to prove it, I can totally lift up the board to show you. Okay? So it's back there. We wrote that down. That's when we broke it up into a system of first-order equations. That was it. Okay? So here, we don't have to think very much. Right? So a lot of the code here is just what my equations are. Just put them directly in. I don't have to think about it. The only thing you really, like I said, the only thing you really have to think about at the end of the day is that initialization. Okay? So we'll save this file, save as. In this case, it just carries where the x information is located. If I were to have a non-constant coefficient, you'd see it in there. Suppose I had, times sine 3x. Well, I could have a function that, for instance, had that in it.
In the general case, we use x as an argument, but in this case, we actually...
In this case, since I had constant coefficients, we can live without it. But you still always have to pass it in. It always expects it there. Okay? So save. All right. So now, that's the first function call. You see how easy that was? That just took care of that guy. Get me my differential equation you want me to work on. We just did. Now it says, give me some boundary conditions to work with. So we just got to do that. Okay? All right, so let's build another routine. File, new, mfile, and function. And I call, we want now these boundary conditions. And what do we want these boundary conditions to look like? I call them BC right-hand side, right? Or BVP, BC, BVP, right? And what I'm sending in here, again, is now what I'm sending in here are two things, the left point and the right point. The values at the left and the values at the right. So let me call these YL, YR. Okay? So remember, we're going to evaluate these at two specific points. And by the way, interestingly enough, if you would like, if you have purpose and need for it, you can specify intermediate conditions in the middle. So you could say, at the left, at the right, it's this, this, and in the middle, I have that. Okay, depending upon your differential equation. So it allows you that flexibility. But for us, what we're doing here, this problem is completely defined by having the left and the right, and there they are. So they come in as left and right, and we can just say, okay, what are my boundary conditions? And I have two functions to satisfy. The first one, if you remember, was at the left, YL, the first component minus 3. That function needs to be 0. Okay? So let's look behind the board. Y1 minus 3 is 0. Y1 minus YL, the first component. Remember, YL is a vector. It's a left vector, has two components, Y1, Y2. The first component minus 3, that has to be 0. Okay, that's my first function to satisfy. The second one is the following. The right, at 1 plus 2 times the derivative, which is the second component, minus 5. That's equal to 0. What's that? YR is the first component of YR, which is Y1, plus 2 times second component of YR, which is Y2, which is my derivative. Remember, if you remember my differential equation, I have this derivative over there, right? Y1 plus 2, Y prime, which is Y2. I brought the 5 over. There it is.
So the second component of Y2 is not you have it 100 points, it's not 100.
No, YL and YR are the values of the vector at the left and right boundary points. There's nothing to do in the middle now.
Okay.
Right? The only thing that comes into this thing is your boundaries at 1 and 3. You've already told it this, right? When you set up that init file, you said, I want to solve this thing. Remember, in our init, we said from 1 to 3 and 10 points. 1 to 3 are your boundaries now. And that's what it thinks YL and YR are living. Yeah?
So if you did want to put an intermediate condition in there, would you need, how would you feed in the X information so that it would know where that is?
I'm not sure.
Okay.
I'm just saying you could do it. I didn't say you did it. It's in the documentation somewhere. All right, we could probably hit that up later, maybe. We'll see. All right, but right now we got so much business to do. I might not get to it. All right. Let's save as .m. Save. So now what I've done, I've specified the boundaries. I've specified the functions. So now I have the functions, I have the boundary conditions, and I have this thing here which calls it all. Initializes, makes my guess, which right now I'm just saying, the solution is 0 everywhere. And of course you know it can't be 0 because what's the left boundary? 3. You cannot satisfy the boundary condition with your solution being 0. Nor can you satisfy this. And so 0 is clearly not a solution, but we're going to guess it anyway, and we're going to see what happens. And let's go ahead and push this play button right there. Okay, now what this is are two functions. The blue is y1. The green is y2. So what I'm going to do is just plot the first column. This is y. So y2, remember, is the derivative. So what I was plotting there is the function and its derivative. So if we just do this. Oh, what did I do? Oh, I think maybe I have it ordered wrong. I think I have to do, yeah, first like this. Sorry. First row. I have it in rows. Okay. There's my solution. Check it out. Nice, huh? Now, by the way, I could have written that one down, but you can see it just did it. What's this boundary condition over here? 3. Remember, I guessed the solution to be 2 straight lines. And it iterated very quickly, by the way. And it got me to this solution, which satisfies the boundaries and the solution itself. Okay? So, fairly simple. All right. So now let's ramp up the problem a little bit, because we have to. Let's do something a little fancier than this here.